When evaluating modern text-to-speech architectures, especially in underrepresented languages like Urdu, researchers typically rely on standard human listening tests to determine success. But resting an entire evaluation on a single metric leaves massive blind spots in our understanding of a model's true capabilities. Looking at this diagram, audio evaluation splits into two distinct pathways. The first is subjective naturalness, measuring how listeners perceive the generated speech. The second measures objective reference similarity, testing the strict mathematical alignment against the original audio. Recent studies on Urdu TTS systems reveal a critical insight. These two measurements frequently contradict one another in modern neural models. A high score in subjective listening does not guarantee a precise acoustic match. This discrepancy requires researchers to rethink how we grade synthesis quality entirely. Perceived audio quality and true human authenticity are completely separate evaluation objectives. Verifying one does not verify the other. To solve this contradiction, researchers have developed a highly structured methodology to test models across a wider spectrum of criteria. They utilized a domain-stratified benchmark. Instead of testing a model on generic red text, this framework forces the model to generate speech across entirely different communicative styles. It integrates independent layers of analysis, comparing perceptual listening tests with discriminative tasks, acoustic destruction algorithms, and speaker similarity matching. By looking through all these analytical lenses simultaneously, researchers expose where a system actually excels and where it is hiding high acoustic distortion behind a naturally pleasing voice. This matrix maps out the evaluation architecture, starting with 4 communicative domains on the y-axis: formal, conversational, literary, and emotional speech. These domains present unique acoustic challenges that stress test a model's architecture. On the x-axis, we have the testing metrics deployed against them. The first column represents Mushra-style listening tests. These gauge subjective human preference, measuring how naturally the synthetic voice flows to a listener's ear. The second column relies on ABX discrimination. This tests whether listeners can accurately distinguish the synthetic audio from the natural human reference recording. The third column uses Resemblalizer, a tool deployed to measure how closely the generated audio matches the exact vocal identity of the target speaker. The final column tracks 2 mathematical metrics: mean Mel substral distortion, or MCD, and F0 root mean scra error. These calculate strict acoustic distortion and pitch drift. These final mathematical calculations operate completely independently of human perception or bias. They analyze the raw signal. This multimetric matrix proves its value quickly because a model might easily pass the human Mushra test while completely failing the mathematical distortion test. We see this exact dynamic play out when comparing state-of-the-art systems within this framework. The data shows that no single system achieves superior performance across all evaluation dimensions. Looking at this data table, Gemini TTS wins in subjective naturalness with the highest Mushra score of 3.040, indicating listeners preferred its fluency. But watch what happens when we shift to the objective acoustic metrics for Edge TTS. Edge TTS achieved the lowest mathematical distortion and the lowest pitch error. Acoustically, it produced the closest physical match to the original human reference recording. We have a direct contradiction. The model that produced mathematically superior signal fidelity was not the model human listeners preferred. Modern TTS systems force explicit optimization trade-offs. Selecting an architecture requires knowing whether the end user needs conversational naturalness or strict documentable acoustic fidelity. A massive disruption occurs in the data when we isolate the emotional speech domain across all of the evaluated systems. In every evaluated model, emotional speech proved to be the most challenging synthesis condition by a wide margin. The failure spanned multiple metrics. First, emotional speech received the absolute lowest perceptual Mushra scores from listeners. Then, as this bar chart reveals, the mathematical error spiked massively. MCD jumped to 12.03 decibels, and the pitch error skyrocketed to 888.54 cents. Simultaneously, the speaker similarity metric plummeted to a low of 0.5437. The linguistic cause of this breakdown is expressive prosody. Human emotion relies on complex, irregular pitch variations that current neural architectures struggle to model accurately. Emotional speech acts as a severe boundary condition. Until an architecture can map these expressive variations mathematically, human-level synthesis remains an unsolved problem. This brings us to the final, most crucial finding regarding human perception, found in the ABX discrimination results. The listening tests establish that current systems can generate highly rated, natural-sounding audio. However, as this data illustrates, despite those high-quality ratings, listeners correctly identified the true natural reference speech in 90.7% of the trials. This identification rate means the AI-generated speech, while fluent, remains clearly distinguishable from natural human communication. The academic takeaway here is precise. Improving the naturalness of a synthetic voice does not equate to achieving human-level authenticity. This authenticity gap proves that researchers must employ strict discriminative testing to cut through the illusion created by high subjective preference scores. The ultimate contribution of this study is the establishment of a domain-aware, multidimensional assessment foundation for underrepresented languages. To advance the field, the researchers have publicly released their entire evaluation pipeline, the benchmark results, and the reproducible resources required to verify their findings. Future research can expand this framework by utilizing standardized online platforms for listener studies or by mapping these metrics against other low-resource languages. As AI speech synthesis attempts to cross the uncanny valley, rigorous, context-sensitive evaluation is the only way to hold these systems accountable.